Log on, tune in, find out. Another good idea from Cambridge.
Cart, I don't know, but you're here, and that's a good start. We hope you've had the full English breakfast and are ready to last the entire morning. I've put the list of individuals who've been organizing this up in the front. If you want answers, talk to the reception staff. If you want sympathy, you can talk to us. But maybe in the order given there. So I wanted to start the workshop by giving some sort of overview, at least vision, as to how our thinking was about what we're doing here. We've brought three different communities together. Those who are involved with the design of physical experiments and applications and the development of such methodology, as well as those who are involved in one way or another, in one type or another of, let's say, a computer experiment. We're in many cases, not in all cases, but in many cases, the communication between these communities is somewhat minimal. We don't know what the problems are that the specific applications we're involved with drive, what sort of things are of sort of research-worthy interest. There may be solutions for some of these in one community that are just unknown in another community. And part of the problem is that we're trying to understand what some of the details are, at least some significant applications in the various communities. So we know historically physical experiments developed early on. Then stochastic computer experiments have a long sort of history, sort of dating back to World War II and in industrial engineering environments after that, and more recently, deterministic computer experiments. And to say a word about some of the facets of computer experiments that I think are of interest in a common sort of way, from the point of view of scientists, at least, they're the gold standard for determining relationships between an endpoint of scientific interest, let's say, and factors, unlike computer experiments where you have some sort of emulator of an input-output relationship. They're expensive to run. They have relatively few factors generally, each with relatively few levels. Factors with 2 levels are very typical. One thing that is often the case is there's the use of what are called blocking factors to allow inferences about primary treatment factors to be extended to multiple environments. You experiment in cold and hot temperatures and rainy and dry environments and so on. And the same sort of thing happens in simulator experiments. Of course, in physical experiments, you have to randomize because you don't know what other factors might be lurking in the background that you don't know about. Those kind of issues are not present in computer experiments typically. In terms of the things that are important for experimental design, of course, independent estimation of those critical treatment parameters, screening, designed for screening to find important sets or active sets of variables, for efficient, that is to say, small variance estimation of treatment contrasts is important to facilitate prediction and many other goals depending on the particular scientific setting. Computer experiments replace the physical system with some sort of computer simulator, either stochastic or deterministic. The stochastic computer simulations typically are involved with discrete event dynamical systems, and we'll hear a lot about those over the next several days. From my point of view, the majority of these use what might be thought of as macro modeling, that is to say, queuing models to represent traffic in some generalized sense. Of course, auto, but scheduling of passengers or cargo through airports or computer networks or whatever, inventory models to describe the costs and inventory costs and patient or customer satisfaction with the availability of materials, production planning models, and the like. First used in military applications, are widely used in business and in other types of areas that we'll hear some applications during the next several days. The output is random. That's one difference between this and the deterministic kind of computer simulation that we'll see. You observe a waiting time to manufacture something, to deliver a passenger or a piece of cargo, to develop a product, costs associated with that, and various measures of the product or process quality. The output can be real valued. I think more often is multivariate. Sometimes it's functional, most often a time series of some sort. The inputs in stochastic simulation models are environmental, which is to say different environments in which you want to examine different policies. So they're sort of like blocking factors, environmental factors, as well as unknown parts of the model which don't represent necessarily different environments, but they represent uncertainty about how a particular aspect of a macro model works. So the uncertainty about model parameters affects our quantification of the uncertainty in answers that we see. I mean, if we're going to look at a mean response for a particular set of control variables in a stochastic simulation, we have to account for the fact we don't know quite what those model variables are. If we want to understand how the environment affects a particular control set of variables, then we're looking at somehow the variance in the response over the distribution of the environmental variables. And that's an important theme. And it's an important theme also in deterministic computer experiments. So sort of separating these out has some advantages. And of course, there's the whole range of scientific applications that we saw in physical experiments, verifying the model, that is to say, can we reproduce data that we actually see from this kind of system, screening to find active variables, sensitivity analysis, once you know active variables to understand, is the effect linear, are there interactions and the like, how robust is the model output to the random environment or uncertain model parameters, and so forth. How do you optimize system performance? And there's a strong interface with classical statistical methodology, particularly regression-based methodologies, as well as jackknifing, cross-validation, bootstrapping, and sort of validation issues. And design is an important issue here too. The orthogonality of the design to estimate treatment parameters, high-resolution designs, knowing what the aliasing, who's confounded with who in a particular kind of design is important. Deterministic simulators, on the other hand, are a bit different. They're numerical implementations of some sort of detailed physics or biology-based model. We're working on a problem in tissue engineering where pressure in cartilage is being developed as a result of a study of a linear biphasic model, and there's a whole set of couple differential equations which describe linear biphasic interaction. So it's often PDEs or coupled PDEs that you're looking at. The application areas tend to be a bit different than in stochastic simulation models. Climatology, cosmology, engineering, biomechanics, the one I'm most involved with, and life science applications. I mean, for example, in biomechanics, you don't typically run experiments putting 10 of this kind of particular prosthesis in one patient group and another 10 and have a second kind of prosthetic device and so on. You don't make comparisons of that sort. Rather, people study these by means of finite element biomechanics codes that describe stresses and strains at bone prosthesis interfaces. The output is deterministic, at least up to numerical noise. I mean, if I run on a 64-bit machine or a 128-bit machine and so on, there tend to be small differences. The output is sometimes not related to anything you can actually physically measure, stresses and strains, throughout, let's say, a particular body or a particular metal or a particular, let's say, a particular interface of two quantities. You have a tool, you put a coating on it, you want to study the stresses and strains just below the surface of the tool cutting head when you put a coating on it or something. That you can do with a finite element code. You're not going to measure that in a physical experiment. You're going to see when delamination occurs if you put it into some sort of test rig. Pressures, sometimes you can though. Pressures, for example, those are can be measured in analogous physical experiments. So sometimes they're related and sometimes they're just they can be exactly the same. The environmental model and control variables you see in deterministic experiments are precisely the same, though, as we see in other sets of experiments. So there's a commonality there. And the goals here are model verification. To what extent does the finite element or computational fluid dynamics or other model, numerical model, solve the mathematical model? And then to what extent does it represent reality, validation, if you will? So those are two important issues when you're using deterministic computer experiments. There's always some skepticism in the use of a deterministic computer model. I mean, does it represent reality in what sense? What are the biases? How do you measure the biases and whatnot? The issues of screening are the same as those in physical models or stochastic simulations, and so is sensitivity analysis. And how you couple the output from a physical experiment and a deterministic computer experiment is of great interest. And we'll hear about this in the case of stochastic simulation experiments. I've never seen anybody combine data from all three kinds of experimental modalities, though. So optimizing system performance is one thing that's certainly of interest, how you set control variables to optimize it in some sense, taking into account the variability over the environmental variables and so on to formulate the problem in an appropriate way. So the purpose of this workshop is to learn about each community's research. Having some idea of this, we've built into this workshop 3 panels where we have a chance to interact at the level of this room with one another, and we hope informally otherwise. So day 1 is we're going to have a series of talks about substantive applications from the various computer simulation communities, deterministic and stochastic. And we'll have several talks about how validation, calibration proceed certainly in the deterministic computer simulation. There's one late addition to the program. Grant Ryman is going to speak on design for variation, which is the TBA in the first afternoon session. He will be filling that spot. There's going to be a series of posters that are available, I think, beginning Tuesday. And we'll have a preview or storm of those at the noon hour right before lunch. And then late in the afternoon, we'll have a talk about orthogonal arrays, a Rothschild visiting professorship. John Stufkin has been visiting for a month and is going to give a lectureship about orthogonal arrays, an area in which I think every one of us who are in all 3 communities have use of those type of designs, either to produce independent things or, in the case of certainly deterministic computer experiments, as an aid to producing space-filling designs. There's a wine reception, which I hope no one will forget, after the talk, around 6:15 or so, whenever it's finished. Day 2, we're going to have an emphasis on design and screening. There'll be a panel discussion about interface between the 2 kinds of modalities based on what we've seen up to then. Then we're going to hear about some specialized problems on day 3, large-scale stochastic computer simulations, the use of kriging, which is common to both deterministic and stochastic computer experiments. We'll find out what goes on in the stochastic computer simulation. And then in the afternoon, there's free time to tour Cambridge. We prepared a handout which will be available at the registration desk when you came in, I think beginning around noon or something today. It will point out several places that you might want to visit that might be of interest. There's probably something for everybody's taste. We're going to talk on day 4 about input uncertainty, about robustness with respect to choice of control variables, uncertainty quantification, kriging. So it'll be a methodology sort of oriented, and then there'll be a panel discussion to talk about input uncertainty, how that's handled in the various communities, what the experimental and the closely related issue of experimental robustness. And finally, on day 5, prediction methodology, multiple models, and then a final panel discussion, the purpose of which is to try to summarize 5 days of interface and try to identify what are the challenges that are common, what are the things that might be movable from one community to another community, where is new methodology needed. So where are we going, in other words, in Latin? And let me just end by putting up one of the sites that are of some interest to statisticians at least. In the center is, well, this whole thing is part of a stained glass window that's in Keyes College. That's how you pronounce that, Keyes, which is actually Gonville Keyes College, which is one of the sites that we'll label on the map that you're going to pick up. It's open until 2 o'clock, I understand, on Wednesday, so one can go down and actually walk in and see this dining hall, which has stained glass windows that are associated with the various fellows, most of whom are actually Nobel Prize winners, and the stained glass windows dedicated to the contributions that they made in science. This is the first one. Left one is Crick, Fisher, and then this last one is James Chadwick. So this is a 7 by 7 Latin square in 7 colors. So it's a very famous window among statistical types, and of course the DNA. Crick and Watson. And you can, of course, visit the Eagle, which is the famous pub where Crick and Watson actually did all their work. So with that, let me invite our first speaker.
Before you do
yes,
that, Tom,
please.
may I just make, there was one important thing that you forgot to mention was a conference dinner on Wednesday evening at 7:30 at St. Catherine's College. It's on your schedule. But
And there'll be, I think there'll be a map of where St. Catherine's is someplace.
it's probably in the folders.
Probably in the folder. Okay, so.
Any eligible list there?
Yeah.
Yes, I think so.